Hello and welcome. My name is Johannes Licht. I'm a PhD student with Torsten Hoefler's lab at ETH Zurich, and I'm going to talk about StencilFlow, or how we can get sustained teraflop level performance on an FPGA using Python. So our friends at the Swiss Meteorological Services use this weather model called Cosmo in order to do weather prediction in production. And Meteo Swiss, they were ahead of the curve in that they were one of the first weather services to start incorporating GPUs into their production systems to do the weather simulation in practice. And this project was part of an effort to explore what other options or what future options for hardware acceleration we could use to further accelerate weather production codes such as these. Now the observation that went into this is that if we look at these weather simulation codes, they consist of a lot of different components, but a major one of these components are large stencil programs such as this one, where a lot of heterogeneous stencil operators compute on a lot of different inputs with complex dependencies between them, such as this one. And the idea or the key observation was, what if we could pipeline these dependencies in a fine-grained manner on a spatial computing architecture such that we could exploit the parallelism not only in the width of the program, but also the depth of the program using pipeline parallelism. So we would want to squeeze this thing onto an FPGA. So the philosophy of StencilFlow is take this whole architecture, stream data from the inputs to the outputs in a pipeline parallel manner, such that the entire program is mapped to a fully pipelined parallel streaming hardware architecture, and then transparently expose this from a high-level scientific DSL so that a high-level scientific user can use this without knowing any of the hardware details that go into programming spatial systems such as FPGAs. Now, what do we mean by stencil operation? You're probably all familiar with stencil programs. We perform updates on a structured grid, which can be one-dimensional, two-dimensional, three-dimensional. Then we perform cell updates, so in this case to an index I, J into an output C, using two inputs, A and B, which we access at constant indices, constant offsets with respect to the center. So for example, here we access two constant offsets, I minus 1, I plus 1, which are the two vertical adjacent dependencies of A, and then two horizontally adjacent offsets of B at J minus 1 and J plus 1. Now if we take a number of these stencil operations and then we piece them together in a DAG, then we call that a stencil program. And a stencil program is characterized by all stencil operations operating on the same grid, which does not mean that they all access the same data or write the same data, but just that they live in the same iteration space, meaning they have the same idea of what the physical output simulation structure is, for example, the horizontal and vertical grid that makes up the domain that we want to simulate the weather over. So the A and B that we're reading in C can either come from memory, or they can come from other stencil operations, like the example here where A and B are themselves stencil operators that feed their data to C. Now the StencilFlow stack operates on this type of programs and has a number of components. I'm going to highlight some of the most interesting points of a few of them. So like I mentioned, the idea would be that this should be used by a high-level user. So at the top of the stack, we have a JSON-based domain-specific frontend, which is usable via Python. So the idea is to only require the minimum number of inputs to be specified by the user in order to recover the actual stencil program. So the user would provide how to get the inputs from disk or from memory, the size of the domain, the operations themselves, and then the actual dependencies between them would be just inferred by the system. So all of this would then be just passed to the Python runtime of StencilFlow, which will take care of the rest of the analysis. So from this, we can then produce the stencil DAG, which we can use to proceed to the next step of the StencilFlow stack, which is abstract hardware mapping. So in order to actually map this to the FPGA, and in order to do this whole streaming architecture that we want to, we need two classes of buffers. So one is internal buffers. So internal buffers are responsible for maximizing the data reuse within each of these stencil operations. And then we need delay buffers that maximize the data reuse between stencil operations. So in the global program and the connections between the different stencils. And the philosophy in order to achieve this fully streaming computation will now be that we want to exploit all available reuse, so that by design, every memory location is read exactly once. So once the memory is into the system, we keep it there, we propagate it throughout the system until it's never needed again. So starting with internal buffers. Internal buffers are what are responsible for holding the data in the stencil operator from the first time it's read until the last time it's needed, after which we can throw it out. For example, with this stencil here, we'll be accessing two offsets in the horizontal dimension, I and j dimensions. We would need to buffer this sort of row in order to until we'd used it for the last time. So we can visualize it like this. We have some data. We have 3 classes of data. We have data that we have yet to stream in, either from memory or from another stencil node. Then we have data that we have read at least once, but that we will need again for one of the other offsets of the stencil, which is this reusable buffer area. And that's what we need to map to internal buffers. And then we have retired data, which is data that we have used in every offset where it will ever be needed, and we can safely throw it away. So then when we traverse, each of these domains are then updated, and only the necessary memory is kept in this reusable buffer area. So for 2D dependencies, we need to buffer rows, as I showed here. Or for 3D dependencies, we have to buffer up to slices. So in this case, we're accessing a point at ijk, but then we also need the offset k+1, which is in the 3rd dimension. And this would require us to buffer this whole 2-dimensional slice so that we can hold it in memory throughout all the time until we need it for 1 k dimension later. If we do this, we gain this property that we want, which is that every cell that is used by stencil operation is only read exactly once and then thrown away when it's not needed anymore, which essentially means that we gain perfect reuse in the program. So the other aspect was global reuse. So once we have all the reuse that we need within each stencil operator, we can zoom out and look at the program as a whole, where there are other potentials for reuse. For example, this needs to at some point read from an input memory. And if we imagine an input memory D, this might be used by more than one stencil. So in this case, D is read by both the A and the C stencils. So what we can do in this case is read D only once and pass it to both A and C. And the other scenario we could have where reuse is possible is if we produce data from a stencil which is then needed by multiple other stencils. So dependencies between stencils that are not just from one stencil to another, but from one stencil to multiple stencils. And we can now exploit this by piping the data between these different stencil operators directly across the chip rather than doing round trips to expensive off-chip memory. So in order to do this, we need delay buffers, and I'll briefly explain to you why delay buffers are necessary. So if we have 3 stencils here, A, B, and C, where the result of stencil A is read by both stencil B and stencil C, then the important thing to keep in mind here is that each of these data connections that are drawn between the stencils represent physical hardware. So somehow we need to pass data along the chip in registers and wires that have a physical manifestation on the chip. And what that means is that these sizes have to be fixed at compile time. So we cannot dynamically allocate memory at runtime on the FPGA. We have to make sure that every data that needs to be buffered on the chip has a physical location for it to be in. So in order to achieve this in practice, in order to make sure that the whole system can run in a pipeline parallel way, there are additional signals in each of these data paths. So each of the data paths between the different stencil operators is not just the path for the data itself, but also 2 synchronization signals that are bidirectional. So we have an empty flag, which tells the communication that if the producer does not have any data ready to send, and a full flag, which tells the communication that the consumer is not ready to consume anything. And in order for a transaction to happen, neither of these flags can be set. So we need to make sure that the producer is ready to produce, so it has data available, and the consumer is ready to consume, which means that it has buffer space available. So if you now pencil in the delay buffers, there will be a delay buffer here of size 2 for the stencil B, because it needs these 2 indices of A that it needs to evaluate one cell of its computation. We do the same for C, where it needs 1 value of B and 1 value of A. Then we can try to see what happens when we start pipelining data through the system. So if A produces a first value A, then this needs to be sent to both B and C. So if we do that, the first value in B will populate 1 slot in the internal buffer of B, and in C it will populate the only slot in the internal buffer of C. Now we produce the next output of A. We end up in the following situation. C cannot compute anything yet because it's waiting for data from B to arrive, so the empty flag is set here. B cannot compute anything because it's waiting for the next value of A to arrive, so the empty flag is set here. However, A cannot send more data right now because on the right-hand path, on the path to C, there is no space to send it. So the buffer on the C side is full, meaning that A cannot send to C. And what this means is that we actually end up with a deadlock, which is not immediately intuitive since we're working on stencil directed, supposedly acyclic graphs. But once we go to hardware, we see that because of these empty and full flags that are bidirectional, we can actually end up with a deadlock in the system, and meaning this is something that we have to address explicitly in order to prevent this from happening in practice. So what do we do? Well, this is where we need delay buffers. So we can insert buffers throughout the design that can buffer these values until they're ready to be used. So if we inserted a buffer here on the path between A and C, then we could now process this next value of A, send it along, so it would go into the second index and the delay in the internal buffer of B, and then populate this delay buffer on the path between A and C. And now B would have everything it needs in order to compute the first output, which would populate the input of C and then allow C to continue its computation. And then we could continue streaming. A could produce the next value. The internal buffer of B would be updated. The delay buffer would be updated, and so on. So if we do this, we can reach a state where we avoid these deadlocks and where all of the paths can stream simultaneously. So we gain all the parallelism in the system once the initial ramp-up phase has been completed. So all these buffers have been saturated. Then we can sort of continue to stream for the rest of the program. And the size of these delays, so the size of which the size of these buffers will be inferred from, is decided by two things. Decided by the internal buffer size within the stencils on the path, so how many values B in this case needs to buffer before it can start actually streaming computations, and the computations themselves, so the depth of the pipeline within B, so the operations it needs to perform, which will also delay the signal until it can actually output a value that is ready to be used by C. So that's the abstract hardware mapping, and now we sort of on a conceptual level have a design which we can fully pipeline and that will not be deadlocked, and that can eventually stream all these different stencil operators at the same time. So now we need to actually start mapping this to something we can compile, and for this we use the data-centric parallel programming framework DACE as an intermediate representation as a code generating framework for StencilFlow. So once we have this abstract hardware mapping, we take this and we build an STFG from it, so stateful dataflow multigraph, which is the intermediate representation used by the DACE framework. And the reason why this is a good fit for something like StencilFlow is that, first of all, STFGs have the ability to be compiled directly to FPGA code, so we gain access to a powerful code generator. And then dataflow, being a native concept within this representation, is a way for us to express this dataflow in the stencil computations in a native way. So STFGs expose these pure dataflow states where everything inside only operates via dataflow. And we can also map these sections to parallel stencil operations. So components within this graph, within these dataflow sections, will be compiled to distinct processing elements on the FPGA, so parallel modules we can use to achieve this pipeline parallelism that we want. So once we have this high-level dataflow graph, we then need to actually expand and generate code for it. So returning to the STFG IR, we had these nodes, B0 through B3, and these are what we call library nodes. The library nodes are a way of expressing the what needs to be computed rather than how they're computed. So these library nodes essentially represent the abstract behavior in order to evaluate a stencil. So within each of the library nodes, we will have some domain-specific information that can tell eventually an implementation what it needs in order to generate the how, such as which fields are accessed and which offsets into that field, the boundary conditions that we set from the input, as well as the computation itself. And then once we actually want to generate code for this, these are then what we call expanded. So each of these little nodes are expanded into a subgraph that actually implements the specific stencil operation on the target architecture, for example, in this case on Intel FPGAs. So what does this mean? So when we expand this, we essentially take these little black boxes and we blow them up into some arbitrary complicated subgraph, which will end up expressing the actual computation that we want to do. So within each of these subgraphs, we have designed a specific implementation that targets Intel FPGAs because we want to specifically target the things that will make this fast on an Intel FPGA. So one of the important things we need to do is we need to generate perfectly nested and fully pipelined loops. So this makes sure that we get pipelines that run continuously throughout the design and don't have any extra buffering phases that don't perform useful computations. And then we can exploit architecture-specific features such as shift registers, which is a powerful abstraction on Intel FPGAs in order to express the kind of buffering patterns that we need to implement stencil operations. And then once we do that, we can use the code generator of the DACE framework to emit structured high-level synthesis code that will then be sent to the compiler and actually be compiled into efficient hardware. So that was a brief summary of the whole StencilFlow stack. And now let's take a look at what this actually performs like. So for this plot, I'm showing scaling up the number of stencil operations for simple iterative stencils. So these are the types of stencils that you typically see evaluated in HPC workloads. So stencils that just perform the same operation over and over again in sort of a with an outer time loop. And the typical way of accelerating this on FPGAs is to time tile, so execute multiple time steps in a row. So we can emulate this within the StencilFlow framework by essentially just replicating the same stencil many times after each other, where each stencil is dependent on the previous. And if we scale this up, we see that as we increase the amount of parallelism, we get performance up to when we've exploited the full device here at 570 gigaflops for a vectorization with a 4, but then we also continued scaling this, so we scaled across 2, 4, and 8 FPGAs to get all the way up to 4 teraflops across 8 FPGAs for this stencil code. And we implemented communication using the streaming message interface framework, which is a framework for achieving MPI style communication, but through a streaming interface, which is the native programming model for FPGAs. So then we also pushed the performance of the individual iterative stencils on a single device to see how high we could get. So here we compared to state-of-the-art performance of a hand-shoot implementation, which is in the order of 900 gigops per second. And what we show is that StencilFlow can, from this fully code-generated code that starts from a high-level input, can be on a par or even outperform the hand-shoot encodes, so pushing 1 teraflop per second here for single precision, and in particular doing this with a fully automated stack starting from a Python front end, assuming you have the patience to wait for the 12 hours for the FPGA architecture to compile, because that is still the state of FPGAs today. So returning now to the weather codes, we essentially took the biggest weather stencil program that we could find within the core of the Cosmo weather simulation framework, which is called horizontal diffusion, which we obtained from the generic DAYS framework frontend, meaning not one specific StencilFlow, and then used that in order to recover the StencilFlow DSL, so the JSON format, which we can use as an input to the StencilFlow stack. Now this we use to generate a DAG, so after a few optimization passes, it looks something like this. Now this graph contains 130 floating point operations per grid point, including complex operations such as square root and min-max operations. It also contains 20 data-dependent branches, so branches that will actually do different operations depending on the value of the inputs, leading to a full arithmetic intensity of 65 18th operations per byte. So evaluating this in the Stratix 10, we ran into a fairly significant memory bottleneck. We saw performance of 145 gigabytes per second, which is about 52% of the roofline performance that is implied by the arithmetic intensity that I mentioned a moment ago. Now, compared to a CPU implementation, this is about a 5x speed up, but noticeably with a much better exploitation of the actual bandwidth available. And just to mention here, the CPU and GPU implementations which I present here are not naive programs, but rather highly optimized codes emitted by a specific stencil optimizing weather framework called Dawn. Now, looking at the GPU performance, we compared to two different GPUs. We compared to the P100, which is a generation that is comparable to the Stratix 10, so similar release window and process architecture. And here the Stratix 10 is still behind. The P100 performs about 210 gigabytes per second, primarily due to its much higher effective bandwidth. And then the V100, which is the next generation of GPUs that the Swiss Meteorological Service is currently upgrading to, is again way further behind, again with an even larger bandwidth, but also higher percentage of utilized bandwidth. But the important thing to notice here is this percentage of the roofline performance. So what we did see was the FPGA was very good at utilizing the memory that was available to it. So in order to sort of stretch this argument and see how it would behave if we did have more memory available to us, the current device only has DDR4. So if you imagine we had something like HBM, then we try to rerun these experiments, but pretending like we have infinite bandwidth, essentially by simulating all the inputs to the program by just producing them on the chip rather than reading it from memory. And here we saw that the FPGA performance went to 513 gigabytes per second on this horizontal diffusion program, which outperforms the P100 by quite significant margin, but still falls short of the V100. So what we sort of saw from these experiments were that first of all, Zurich 10 was held back by insufficient bandwidth. So the balance between compute and memory bandwidth is not good on these FPGAs for these types of weather applications, but also that the FPGAs are quite good at exploiting the bandwidth that is available to them. So once the memory gets onto the chip, then doing a large number of computations comes very cheaply. So the question is just of how much data we can actually get there. However, this does require quite a lot of pipeline parallelism. So the reason why we ended up being memory bound here was because even with this large complex application of horizontal diffusion, there still wasn't enough pipeline parallelism in the program to conquer the memory bottleneck that we see here. Since this was an effort to provide a mapping to hardware architectures that would be accessible even for high-level users, we put significant effort into producing a artifact that is actually usable. So all our code is available on GitHub with high-level Python interfaces and documentation of how to use it. And if you're interested in this sort of work, or you're working with Stencil's FPGAs yourself, we would love for you to go try it. And particularly, we would love for you to try to break it so we can find the holes in our system and see what we still need to support in order to be able to cover all the potential use cases. In summary, I presented a high-level frontend, which can be used by a non-hardware savvy user in order to target the architectures emitted by StencilFlow. I showed you how we need these two classes of buffers, internal buffers and delay buffers, in order to achieve perfect reuse on the FPGA to achieve these fully streaming architectures. I showed you how we target FPGA-specific features when we want to compile for Intel FPGA, such as perfectly nested pipeline loops and shift registers using the Days code generator. I showed you how architectures submitted by StencilFlow are competitive even with hand-tuned codes on traditional time iterative stencils, as well as being able to tackle very large and complex stencil programs such as these large weather applications. And all of our work is published as an open source artifact that we would love for you to actually go and try use and see if it's useful for your work. So with that, I would like to thank you for your attention. If you want to go check out StencilFlow, the link is here. And a special shout out to the Paderborn Center for Parallel Computing, which has awesome FPGA hardware and networking setup that we use to perform these experiments.